I'd like to welcome everybody to the third webinar in the series that I'm sharing. We'll be having another one later this year to complete this series. This particular webinar is on evaluating chemical compatibility of GCLs. This is an issue that many consultants, labs, practitioners have to deal with when considering to use a GCL in many different applications, particularly in non-standard applications. And there's a lot of nuances to chemical compatibility testing and assessment that we're going to talk through today. And what I hope to achieve at the end of this webinar is that each of the participants feel like they understand the key issues, understand how they could specify a test for a testing laboratory to evaluate a GCL with a potential leachate, and also understand how to select different products in the context of the leachate that needs to be contained. So just a little recap on where we're at. This is a 4-part series that we dreamed up last year. It's been a lot of fun. This is the third part to it. The first part really was just fundamentals of GCLs as hydraulic barriers. The second webinar was on bentonite-polymer composite GCLs, some of the newer products that have been available for about the last 10 years with a blend of sodium bentonite and different types of polymers that are really intended for more aggressive conditions. Today, what we'll be talking about is chemical compatibility testing. We've got a leachate, we have a GCL. How do we run tests to demonstrate that that GCL is chemically compatible with that liquid? And then later in the year, probably around the May timeframe, we'll have a final webinar in the series talking about lessons learned from case histories. One of the fortunate things I've had in my career is to interact with practitioners and owners in a variety of different cases, some very positive, some not so positive, where we've looked at different case histories and understood why GCLs function the way they did in those applications. And we'll be looking at that later this year to wrap up the series. And if there's interest, maybe we'll repeat this again next year. One of the things I did want to mention, I did mention this early before we start off, is that everybody who participates will receive a certificate of completion for continuing education credits issued by the University of Virginia. An example here shown. Please make sure you're registered and that your name and email address on the registry is correct. I use that list to get the certificates issued. I will post them on a file share for participants to download. I will also be posting this presentation and the references that I cite in the document as well on that same file share at 2 different times, but they will be posted on a file share for everybody to download, and they're all free of charge as we've been doing. So what are our topics for today? Let's go over what I'd like to achieve. First of all, what is meant by chemical compatibility and why is it important? And then second, how do we evaluate whether a leachate and a GCL with sodium bentonite are chemically compatible? A conventional GCL, what tests do we run? Are there index tests that we can use to get a screening assessment? What type of hydraulic conductivity tests do we need to run under what conditions? And then finally, we're going to close it talking about the methods that we've been developing and using for conventional sodium bentonite GCLs really for the last 25 years now, maybe 30. Do those same methods apply to BPC-GCLs or bentonite-polymer composite GCLs? And are there some nuances to those materials that we need to think about when conducting chemical compatibility testing? And as you can mention, the way I emphasize that, there are nuances that we need to consider. So let's begin. Geosynthetic clay liners are really, I keep thinking about how remarkable these products are. We take a barrier system like I show here, and I'm going to turn my laser pointer on, yay, where I've got a compacted clay line barrier and a composite liner that may be 0.5 meter to 1 meter thick. And I'm going to replace it with a barrier that has comparable performance that when it's hydrated in the field probably is 8 millimeters thick. So 10 times thinner barrier system that is equally effective and more significant is that it's a lot easier to construct. We can construct a GCL composite liner much faster than we can a composite liner with a compacted clay barrier. Simpler, more reliable, more predictable than a compacted clay composite liner when deployed under the right circumstances. Pretty remarkable materials. We use them in liners, and that's going to be a lot of our focus today, is in a liner application where we've got a GCL at the bottom, a geomembrane on top of that to form a composite liner, and then a leachate collection system of some sort. Here, this example just with a geocomposite drainage layer, and then protective soil and waste. So, but a GCL barrier as the base, the final frontier, you might say, in that lining system protecting groundwater, replacing the conventional compacted clay liner. This is the most common application for chemical compatibility testing because this waste that we place on top of the barrier system and on top of the leachate collection system generates leachate. That leachate contains chemical constituents which may interact with the GCL. It may be favorable interaction, it may be an unfavorable interaction. And that's really the topic that we're going to be studying today, is that interaction. We could do the same type of evaluation for a compacted clay layer as well, and often we do, although that's not the topic for today, and probably not as interesting. Other applications for GCLs and final covers, just flipping that barrier system around and using it on the surface as a cover system. Again, a GCL, a geomembrane, a drainage layer, and then surface protection layers on top of that. This application as well can have chemical compatibility issues. We're not going to talk about those these days. They tend to be subtle and more nuanced. But when we talk about case histories in the 4th webinar series, we'll come back to that topic and talk about it specifically for GCLs used in final covers. So we won't be covering chemical compatibility issues in covers today, but we will come back to that later in the year. So let's dive in. What is chemical compatibility? I think that's perhaps where we need to start, is defining what this term is. I think there's a lot of confusion and perhaps debate about what we mean when we use this term. But from my point of view, GCL is chemically compatible with a liquid to be contained, for example, a leachate, if the hydraulic conductivity of the GCL remains sufficiently low for the intended application. That's important, sufficiently low for the intended application when the GCL is in chemical equilibrium with the liquid. So we're going to allow the GCL to come in chemical equilibrium with liquid, hydraulic as well. I take that almost for granted as a prerequisite. And does that GCL retain sufficiently low hydraulic conductivity for the intended application? That doesn't mean it necessarily has to have the hydraulic conductivity to water, just sufficiently low hydraulic conductivity for the application at hand, the containment system for which we're designing it. And that's going to be very much material specific, or let's say waste specific, and perhaps industry specific as well. The chemical compatibility largely focuses on hydraulic conductivity. That's the context and the paradigm under which we've been working for decades, but it could be extended to other properties as well, although not commonly, like internal shear strength, interface shear strength, etc. That extension could be made. It's not common and will not be part of my discussion today. Given that hydraulic conductivity in chemical equilibrium with the leachate is important, it's really important for us to come back and talk about what makes a GCL impervious. And we're going to see in the next several slides several of things we talked about in the last 2 webinars as well. Essentially the interaction between bentonite and the hydrating liquid or the permeate liquid through which is flowing through the GCL. It's that interaction, that geochemical interaction between the bentonite and the liquid that controls the hydraulic conductivity. And for us to understand how to evaluate GCLs and how to assess chemical compatibility, we have to really have a sound grounding in the principles that affect the geochemical principles that affect the hydraulic conductivity of GCLs. So I present this each time in each one of these webinars because I want to come back to these ideas because they're so fundamentally important to understanding how these materials behave. So I have this sketch here that we've looked at before in previous webinars where we have a GCL like we get it off the roll. And this is a conceptual diagram, not a photograph. But in this particular example, we have two non-woven geotextiles and casings, granular sodium bentonite. This could be granular, it could be powdered, it could be a well-graded bentonite, depending on the different manufacturing process. But it is a particulate material. It's a granular material. And that material in this GCL in the drawing in the upper right doesn't look impervious. In fact, we see lots of large visible pores between the granules of bentonite. In fact, if those granules don't swell and transform, this product will be very impermeable. It almost looks like two geotextiles carrying a sand. And in fact, if it doesn't swell, it will have a hydraulic conductivity not too different from sand. And I use an operative word there, swelling, and we're going to get back to that. But what must happen for a GCL to become impervious or to have very low hydraulic conductivity, to be more specific, is for those bentonite granules to transform from granular particulates that look like sand to a gel like we see here in the bottom. They have to swell and fill the voids between them, creating a truly microporous or nanoporous material that has very small and very tortuous pores that drive the hydraulic conductivity down to very low levels. If we achieve swelling, the hydraulic conductivity will be very low. If we do not, the hydraulic conductivity will be very high. And so that issue in itself is just fundamentally important to understanding these products and how they function. That mechanism is illustrated here in this slide. If we think of just taking a subset out of that drawing I showed in the previous slide where I've got sodium bentonite granules, and on the left here in drawing A, the granules have swelled and filled the voids. And the pathway through which the liquid flows is very fine and very tortuous and irregular, and the hydraulic conductivity is very low. If they do not swell and those intergranular pores remain open, the hydraulic conductivity will be high. Very simple. It swells, it has low conductivity. If it doesn't swell significantly, the hydraulic conductivity will be much higher. Well, why is this so important with bentonites? And we've talked about this before, and we need to come back to it because the mineralogy of bentonite is particularly important. Bentonite is primarily Montmorillonite, a special clay mineral. It's made up of stacked 2-to-1 sheets. And what's special about these 2-to-1 sheets, we call these 2-to-1s because they have two silicon tetrahedral sheets sandwiching a gibbsite octahedral sheet in between. They create a 2-to-1 unit, and it's adjacent to another 2-to-1 unit. And what's unique about Montmorillonite is they can separate. That these units can separate, water molecules can make their way in, and that's what causes bentonite to swell. And that water molecules move into that so-called interlayer region, forcing the sheets apart, creating large volumes of relatively immobile hydrated water molecules surrounding the mineral surface. These mentioned they're 2-to-1 minerals, that interlayer separation occurs. They're also another attribute is once that separates, the surface area of Montmorillonite is enormous, 800 meters squared per gram, like a football field per gram, an enormous amount of square meters per unit mass. It also has a high negative charge. So not only does it have a large surface area, it's got a high negative charge, so it's really reactive. And that makes the bentonite behave in very special ways when in contact with different types of solutions. In different ways than almost no other clay mineral will behave. And that's why it works so well in GCLs and other environmental applications. This is a busy graph, and I'm going to talk through it fairly quickly because I've shown it before. But this is kind of the fundamental graph that was developed back in 1957 by a clay scientist called Norrish, showing how the swelling or spacing of those plates varied as we changed the chemistry of the solution surrounding the bentonite. And it's kind of got wacky units to it. This on the y-axis is pretty simple, what we call D001 spacing. That essentially describes that inner layer space, and we could just as well just call this swelling on the y-axis, with high swelling up top, low swelling down here at the lower left-hand corner. The x-axis is a little unusual. It's 1 over the square root of the concentration of the hydrating liquid. In Norrish's experiments, it was sodium chloride that he was using, but it's 1 over the square root of the concentration, and there's reasons for that that come back to equilibrium, solid liquid geochemical equilibrium conditions. But it's also a way to linearize the data, and I think that's one of the reasons why he picked it for this graph. But one of the things that he showed was particularly important is that there's a wide variation in swelling that depends greatly on the chemistry of the solution that's contacting the bentonite. If we have a very dilute solution way over here on the right-hand side of the x-axis, I show that as dilute in the upper right-hand corner, we get lots of swelling, lots of swelling. On the other hand, if it's very concentrated, we get very little swelling. All right, so in dilute solutions, we'll get a great deal of swelling, probably low hydraulic conductivity. Concentrated solutions suppress swelling, perhaps much higher hydraulic conductivity. The other component that Norrish talked about was that there's 2 different elements or components to swelling. There's crystalline swelling and osmotic swelling. And it's really that osmotic swelling is that greasy, moist texture that swollen bentonite has in a GCL or another application. That osmotic swell occurs predominantly when the bentonite surface is associated with monovalent cations, things like sodium, potassium that have +1 charge. On the other hand, if the surface is predominantly polyvalent, we'll end up with crystalline swelling only. So if we have predominantly polyvalent or a very concentrated solution, we'll have very little swell. If we have predominantly monovalent and or a dilute solution, we'll end up with high swelling. And that's important as well, as we'll see through as we look through the geochemical interactions that occur during chemical compatibility assessment. Perhaps most important, I'm going to go back to that slide for a minute. Chemistry matters. Chemistry matters. A lot of geotechnical engineers avoided chemistry. Geoenvironmental engineers are at that nexus between geotechnical engineers and environmental engineers. We've had to learn to love the chemistry because it's really important. The chemistry matters. And just to illustrate this practically, I always like to show this slide because I think it illustrates the principles really well. I've shown this before. If you recall the historic GRI GCL1 swell test, where we took a Proctor mold and we would put a thin layer of bentonite in the bottom of the mold, essentially the same mass per unit area as in a GCL. And then we would pour the hydrating liquid on top of that bentonite. And there would be a plate in there, and remember LVDTs that we use to measure swell. Now we use we use LVDT now. We used to use dial gauges back when these first got started. We measure the swell of that cake of bentonite in the Proctor mold. And that's what you're seeing here, these cakes of bentonite. And then the top one is a sodium bentonite where the swell test is conducted with DI water. We get crystalline swelling, we get osmotic swelling, poof, it swells up to about 40 millimeters in this particular experiment, where it started off probably about 6 millimeters thick. So it has really swollen. It's a gel. There are no visible macro scale pores in that material. If we did the same exact experiment with a 50 millimolar calcium chloride solution, so we're going to dissolve calcium chloride in deionized water, pour that on top of the bentonite in the GCL-1 swell test. Exactly the same experiment, everything the same. All we've done is changed the chemistry of that water. We get a very different outcome. We see a very thin patty. It looks like sand particles. You can see the remnant granules. It doesn't swell. And in fact, you can imagine we see lots of visible pores. That's going to be much, much more permeable than the upper specimen. If we look at things close up, it looks more like this. On the upper graph is so-called crystalline and osmotic swelling of a sodium or a monovalent rich solution where we get great swelling, no visible pores between. You can still see the remnant granules, but we don't see the visible pores. On the other hand, in a divalent environment with only crystalline hydration, we see something that looks a lot like sand, but in fact it's not. It is Montmorillonite. It's just a calcium Montmorillonite or a calcium bentonite. These are both fully saturated. It looks wet in the upper photograph. It looks swollen and moist. The bottom one, you can hardly see it, the moisture. It's not really affiliated with the surface, but they are both fully saturated. Very different texture, very different pore structure, very different flow paths, and therefore very different hydraulic conductivity. Again, the same base material, all we've done is alter the chemistry. We get very different outcomes during hydration, very different pore structure, very different hydraulic conductivity. Well, one way that we measure that, we use D5890 swell index test. Many of you run a test like this. This is a very simple, wonderful test that really provides us a lot of information about sodium bentonite. We take the bentonite, we grind it, we fill a 100 ml graduated cylinder with the hydrating liquid up to about 90. Then we drop in our bentonite very slowly and allow it to settle down through the water column. And as it settles down, it begins to swell. And then we top off the graduated cylinder to 100 mils at the very end. But you can see what we're putting into that graduated cylinder is about 2 grams, a tiny amount of solid volume. And it swells over here, at least in DI water in this particular application, up to about, looks like about 16 or 18 milliliters. This is actually not a very high quality bentonite. We're getting what looks to be significant swell compared to the dry material, but in fact, a really high quality bentonite might be on the order of 30, so almost double what we're seeing here. But a very simple, elegant test, actually developed, as I understand, in the pharmaceutical industry and not in the geotechnical or geoenvironmental realm. So I just put a couple of lines up there to illustrate where the current swell index of this material is and where a really high-grade bentonite might be. Well, as you might imagine, that swell index is indicative of those geochemical interactions we talked about, and whether we'll get a great deal of swell if the geochemistry is appropriate for the bentonite to hydrate and swell. On the other hand, if the geochemistry is not appropriate, we'll get a much lower swell index in that experiment. And you might imagine, since that's the granules that are changing size and shape and filling the pores between them, that we get a correspondence between hydraulic conductivity and free swell or swell index measured with this technique. And that's what we show here in this diagram. This is actually a diagram that we created originally in, believe this or not, 1999. And then updated in 2004. So this diagram's almost 20 years old in its current state. So these principles have been around for a long time. They are time tested. One of the things that we see here is I have 2 different lines, and both for these experiments I show with red, green, and blue, I have one line that relates hydraulic conductivity of the GCL to swell index. And as we see, when the swell index is low, the bentonite's not swelling, that GCL is very permeable. And as the swell index goes up, the hydraulic conductivity goes down. It becomes very low. There's another set of experiments. These are some single species experiments that we did with just a salt solution with just a single cation dissolved in solution, and we get a different line. And it's not so much because we use different cations, but between these two sets of experiments, we use different bentonite. They were done about 4 years apart in our laboratory, and the material that was in the GCLs that we were evaluating at the time had changed. The bentonite source had changed. And so we do see that we will get a relationship between hydraulic conductivity of GCLs and swell index and swelling, but it will be unique to the bentonite that we're evaluating. It will be unique to that material. So while there is a relationship, it tends to be a unique relationship. And if we're going to use something like this to evaluate chemical compatibility, we're going to need to be able to have it for the specific GCL and bentonite within that GCL that we're evaluating. So let's look a little bit more about how different solutions affect hydraulic conductivity. Here in this graph, I'm showing the hydraulic conductivity of a GCL as a function of concentration. Like we were looking at that swelling graph earlier in that discussion with Norris's osmotic and crystalline swelling. And we would expect that as it gets more concentrated, we would have less swelling and the hydraulic conductivity would go up. And that's exactly what we see in this diagram, in this graph. Let's take the divalent or trivalent salt solutions. So they're divalent like calcium with a +2 charge, or trivalent like lanthanum with a +3 charge. And we see that as we increase the concentration, the hydraulic conductivity increases as well. And in fact, as we go from a dilute divalent solution to a concentrated divalent solution, the hydraulic conductivity is changing 5 orders of magnitude. Wow, that's a big change, because that material is changing that much from what we saw in the photographs earlier. We see essentially the same trend for divalent and trivalent cations. Essentially, the polyvalent cations behave the same regardless of whether they're divalent or trivalent. The monovalent ions, or +1 charge, are different. We see the same type of behavior with a monovalent like lithium chloride or sodium with a +1 charge, that we start off low at low concentrations. As the concentration increases, the hydraulic conductivity will go up and ultimately become quite high if it's concentrated enough. That was the same idea that we showed earlier, that if we get swelling and if we have concentrated solutions, we will get suppressed swelling regardless of whether they're monovalent or polyvalent, and the hydraulic conductivity will be high. If we switch, for example, from a monovalent solution to a divalent or trivalent solution at intermediate concentrations, the conductivity will be very different because the swelling will be very different. And we see that swelling effect here in this diagram, which shows this the same solutions, but with in a different context. We see here a swell index on the y-axis, valence of the cation on the x-axis. And we see if we just increase the concentration from dilute here in purple to concentrated in blue, we go from relatively high swell to low swell. We're suppressing the osmotic swell. If we alter the valence as we go from +1 to +3 at a given concentration, we'll also reduce the swelling. That's that same effect. So it's both valence and concentration effects. We need to pay attention to both. The valence effect tends to be more important in dilute solutions and less important in concentrated solutions. And we'll see that again a little bit later. So these basic ideas are woven throughout all of the chemical compatibility assessments, because they really define whether a solution and the cations it contains will promote swelling of the bentonite and low hydraulic conductivity, or will suppress swelling and yield higher hydraulic conductivity. So if we understand how a solution affects swelling of a bentonite, we really understand how the hydraulic conductivity will behave as well. We capture these parameters in terms of 2 master variables: the ionic strength, which is an aggregate measure of total concentration in solution. And it's just what we have is the concentration of each ionic species and the valence of that species. And we just take a product of the concentration times the square of the valence. And that square there is so that with the anions, which are negative, and the cations, which are positive, both contribute to the ionic strength. And we add those up. That gives us a measure of total concentration. And then the relative abundance of monovalent and polyvalent cations is shown by the RMD parameter, which is just the ratio of the total molarity of monovalence divided by the square root of the total molarity of polyvalence. Now that's a little weird to have a square root in the bottom. And it's also weird in the same way that Norrish had that square root of a concentration in the denominator of his x-axis of his fundamental swelling graph. That has to do with the basic principles of equilibrium geochemistry between the liquid phase and the solid phase. And so there's actually a fundamental geochemical principle behind having that square root in this ratio. But it leads to weird units in a lot of reports that I've written and others have written as well. And I often get questions about that. Couldn't you have thought about how to create RMD a little different so that the units would be less crazy, you might say? But they are what they are. Well, how do these parameters affect hydraulic conductivity? Again, let's look at a similar graph as we did before, just slightly different context. On the y-axis is hydraulic conductivity, and I've got this on a arithmetic scale because they've taken the logs of the hydraulic conductivity. The more permeable GCLs at the top, less permeable at the bottom. On the x-axis is RMD, so as we go from the left, will be RMD of 0. That's a completely polyvalent solution. To the right of a much higher RMD, that's a solution that tends to be predominantly monovalent. So we go from polyvalent to monovalent as we go from left to right on the x-axis, less permeable to more permeable as we go from bottom to top on the y-axis. And we see a couple things. One, as we increase the RMD, that the hydraulic conductivity drops. And over a typical range, about an order of magnitude, maybe an order and a magnitude and a half, for over a range of RMD that we might normally see in practice. As we change the ionic strength, we see a much larger effect. And we're going to come back to this again later. But from very permeable up here at half a molar ionic strength to much less permeable at ionic strength that's 10 times lower. So the ionic strength effect tends to be more significant. It's changing the hydraulic conductivity many orders of magnitude compared to the RMD effect, which is really an order of magnitude or an order of magnitude and a half. One of the questions I often get, we're making these calculations where we lump all the different cations together and we group them to some extent by charge. Is the species important? Does it matter whether I've got sodium versus lithium or magnesium versus calcium or lithium, sodium, calcium, and magnesium mixed together? Real leachates are mixtures. And it turns out it's not important. What is important is the relative abundance of the different What is important is that the relative abundance of the monovalent versus the polyvalent cations described in terms of RMD and the ionic strength. Those two master variables are the key elements to consider. And we'll see that in a bit. Another question is often about, well, we talked a lot about just the concentrations, but what about pH? We have a really acidic solution. Is that going to influence the outcome? Or what about a really alkaline solution, like a bauxite liquor we might run into? We've done a lot of work in my laboratory on bauxite liquors in red mud disposal facilities. Well, this graph tells that story. One of the things that we see is for a wide range of pH, the hydraulic conductivity of GCLs tends to be pretty much pH independent, roughly from about pH 2 to pH 12. The pH doesn't have much influence on hydraulic conductivity. Outside of that range, it tends to become more important. And the reason for that actually makes a lot of sense if you think about what's happening. When we get really acidic solutions, we start dissolving the mineral. And the alumina that's in the mineral structure goes into solution. Alumina under certain conditions will have a +3 charge. It will be a polyvalent cation. And accordingly, because it's present in solution, tends to increase the hydraulic conductivity. At the very alkaline side, the very high pH, we get the pH high enough, we've just got a high pH means we've got a lot of hydroxide or OH ions in solution. And for every one of those OH ions that's in solution, we have a cation associated with it. So a common alkaline solution that we run into in industry is sodium hydroxide. And when we have a very alkaline sodium hydroxide solution with a lot of OH ions floating around, we also have a lot of sodium ions floating around, a very high concentration of sodium ions, and that too will cause the hydraulic conductivity to increase by suppressing osmotic swell. So the pH effects tend to be important at the extremes, but they're not really driven per se by the pH themselves, but how the pH either affects the mineral by dissolution of the alumina or the cations that come along with a very alkaline condition at the high pH conditions. So pH is important at the extremes is the message from that. Well, let's talk about different liquids and how they might influence hydraulic conductivity of GCLs. I presented this graph earlier, and we're going to use it again today just to kind of look at where we are relative to common behavioral conditions. Right in the middle of this graph is where we got a lot of our early experience with GCLs, with municipal solid waste landfills. And I'll show some data in a minute which illustrates that GCLs tend to be very impermeable when contacted with MSW leachates. That's important because that provides us with some anchoring on this graph. That says if we have things that look like MSW leachates or perhaps are more dilute, that they're likely to result in good swelling and low hydraulic conductivity as well. On the other hand, if we have things that are much more concentrated than MSW leachate or much more divalent, then we might have a more challenging condition with less swell and greater hydraulic conductivity. So we do get low hydraulic conductivities right here in the middle. And you might imagine too, if we went down this cluster of data, that in this region here I'm showing with my laser pointer, we would get low hydraulic conductivities too. On the other hand, if we're so this region here would have low conductivities. But let's imagine we have MSW leachate. Now we step into something that's similar in ionic strength, but much more divalent, like we see in some of the low-level waste leachates for disposal facilities that use a lot of grout to stabilize low-level waste. Much more permeable here because similar ionic strength, but much more divalent or much more polyvalent and a lower RMD. We go to the right and up, bauxite liquor, flowback water, incinerator ashes, some CCP leachates will end up with much higher ionic strengths, potentially higher or more potentially more divalent conditions, and also getting high hydraulic conductivities as well. So these guys, we got to pay a lot of attention to, and we have to pay attention to things that deviate on the low side of the graph, even if they're similar in concentration to MSW leachates. Here's the example I promised I would show. This is just data from MSW leachate for different leachates from different facilities. I noticed I've got some funny numbers here in the background. I don't know what those are. Please ignore those that seem to be behind the caption on the x-axis. We ran these tests actually for several years, very long-term experiments, some of them 7 years long. We ran them with DI water, with conventional leachate from a conventional MSW landfill, no bioreactor effects or leachate recirculation, just traditional dry tomb methodology. And then we had a whole series of bioreactor leachates as well. And we were doing this work to evaluate whether there was really much sense in some regulations that preclude using GCLs and landfills that recirculate leachate. And what we found was that in all cases, the hydraulic conductivity was very, very low. It did increase somewhat over time. The final equilibrium hydraulic conductivity was about a factor of 2 higher than the hydraulic conductivity at 1 year. But in the end, when complete chemical equilibrium and up to 7 years of permeation, all of the MSW leachate, all the GCLs permeated with the MSW leachates had very low hydraulic conductivity. And that's consistent with our experience in the MSW landfill industry. Why is that? Well, landfill leachates tend to be monovalent solutions. They tend to be not too concentrated, and they tend to be monovalent. The two primary cations we see, sodium and ammonium, ammonium from decomposition of proteins, creating ammonium in solution. And when we look at the surface of bentonite, that's been exposed to MSW leachate and come to complete chemical equilibrium, we'll find that the ions that are stuck onto the or bound to the mineral surface are predominantly sodium. That's shown here. This graph shows a bar chart for each of those different conditions shown on the previous slide, each of those leachates, looking at what ions are bound to the surface of the Montmorillonite in terms of a mole fraction. Predominantly sodium, and then in second place, ammonium in each one of these bars. It's ammonium and sodium, a little bit of calcium shown here in blue, a little bit of magnesium shown in pink, some potassium as well, but predominantly sodium and ammonium, and never too concentrated, and therefore great swelling, very low hydraulic conductivity. But that's not always the case for other liquids, those ones in the upper right-hand corner. And when we look at industrial liquids, the ionic strength tends to be the predominant variable. And this is some examples for coal ash leachates with two different GCLs in a study we conducted for Electric Power Research Institute several years back. And the thing that we see with industrial leachates is that we can get a wide range of hydraulic conductivities depending on the ionic strength of the leachate. And here, a trona ash leachate, trona ash is a very strong leachate from trona coal combustion residuals. Hydraulic conductivities are very, very high, much lower for other ashes that generate more dilute solutions in the disposal facility. We do see, even in this case, even though ionic strength is the primary variable here on the x-axis, and conductivity clearly is directly related to the ionic strength, that there is a valence effect here as well. If we just compare the typical CCP and what we call low RMD CCP or coal ash leachates, two different conditions, nearly the same ionic strength. The leachate that has low RMD compared to the typical tends to have about a factor of 10 higher hydraulic conductivity. So about a factor of 10 effect from the valence effect, but a much larger effect from ionic strength more broadly. So in an industrial leachate, ionic strength is going to be particularly important. So let's say we've got a leachate and we need to do an evaluation, right? We need to conduct an assessment to determine whether we're chemically compatible. What should we do? Well, the first thing we ought to do, well, we need to get samples of leachate, right? And here's just some examples actually from that recirculation experiments I showed earlier for MSW leachate. They look like MSW leachate, brown and opaque. But the first thing to do is understand the chemistry of these liquids. Send them off to a laboratory or use your own if you have that capacity, and measure the cations and anions in solution. If you have other organic species that are significant in concentration, significant meaning they've got relatively high concentration, not very dilute VOCs, but higher concentration, you might need to measure organics as well. But start off with cations and anions. We do cations by ICP is a common method, inductively coupled plasma. Anions we'll typically do by ion chromatography. These are standard methods. Any environmental laboratory can conduct them for you. At the same time, measuring the pH, the electrical conductivity, and if possible, the redox potential or the EH. Measure all these basic properties and then put them into a spreadsheet and calculate the ionic strength and the RMD, and I'll talk about that in a minute. So we're going to get the chemistry of each one of these. I apologize, I got a little ahead of myself. And the other thing that we ought to do, we're going to send these to a lab, and it's probably going to take about 10 days before we get the geochemistry back. So while we're doing that, we'll measure the swell index of candidate GCLs with these particular leachates. And it's a very simple test to do, takes a little over a day. ASTM D5890, we grind up the bentonite. We drop the bentonite into graduated cylinders I talked about earlier. In that case, the graduated cylinder being filled with the leachate in particular concern. In this example, I'm illustrating a test conducted with a coal combustion product or a coal ash leachate. We've at the same time, and I often do this in my lab, is we'll run a test with deionized water just to get a comparison. And we see here on the left with DI water that the swell index is really great for this bentonite. It's up around 27, 28. With the CCP leachate, same bentonite, just changing the geochemistry of the water. It's a CCP leachate as opposed to deionized water. We're down around 6. It's a pretty strong CCP leachate, pretty high ionic strength, suppressing the swell. And we can imagine the hydraulic conductivity of this particular sodium bentonite is probably going to be quite a bit higher than it would be to DI water. Might not be compatible. We can use a hydraulic conductivity swell index graph like we talked about earlier to get an assessment of what type of hydraulic conductivity we might expect. And in fact, if the swell index is 6 for a sodium bentonite, we probably just stop there. We probably say if the swell index is that low, the likelihood that the hydraulic conductivity is going to be low is pretty small. We won't go any further. We'll look for a different GCL product to consider. Important at this time, if we do draw an inference of hydraulic conductivity from swell index, we use a data set that's relevant to the particular bentonite that we're testing. I illustrate that here with this graph. The earlier data I showed you earlier from Joe et al. And Kolstad, shown here with the black symbols. Another data set for another set of bentonites in blue and red shown here. 2 different relationships, same experiment, but very different relationships between hydraulic conductivity and swell index. We're running the same swell index test, exactly the same, just different bentonite. So it's important to have a bentonite specific curve if you're actually going to take swell index and get an estimate of hydraulic conductivity. On the other hand, if the swell index is very, very low, less than 10, probably less than 12, the likelihood that the hydraulic conductivity will be sufficiently low is probably pretty small. So we probably could stop there. Now, once we get our chemistry back from the laboratory, we should go and calculate our ionic strength and our RMD. Another parameter to consider too is anion ratio. I talked about this for bentonite-polymer composite materials as well. Get the data back, put it in the spreadsheet, have it calculate the ionic strength, the RMD, and the anion ratio. You might say, well, where is that spreadsheet? You may remember that I put this spreadsheet on the file share that I shared after the first webinar series. I will post it again for you to use. You can download it. It's got all the information filled in. All you have to do is plug in the concentrations and it'll do all the calculations for you. Once we understand the chemical characteristics of leachate, we can begin to look at other data and say, based on ionic strength, based on the RMD, should I expect this, and based on the swell index I've measured, should I expect this GCL to have low hydraulic conductivity, high hydraulic conductivity, or I'm not sure, right? And so if it's, certainly if it seems to be it's going to be very high, we probably don't want to go down the road into a great deal of very expensive and long-term testing. On the other hand, if it's much lower, has a potential to be much lower, well, let's go forward. Let's evaluate whether the hydraulic conductivity is indeed low. And to do that, we use a flexible wall permeameter as shown here on this slide. Now, flexible wall permeameter is a very simple yet very elegant device. And I have to admit, this particular drawing is not for GCLs, but for a flexible wall permeameter used for a soil sample. But it's the same type of apparatus, and we'll see some photos with GCLs in a minute. This is just one that we used when we created ASTM D5084 for soils, and I had that diagram and my Word file from that standard, and I gotta admit I clipped it out of there and used it here. But it's a simple device. We have a chamber, we call that a cell, flexible wall permeameter cell, has a top plate and a bottom plate, typically made out of aluminum, has an acrylic wall, we'll see some photos in a minute, plastic wall. Inside it has a bottom platen or bottom cap, a top cap that go on the bottom and top of the specimen, and then we'll encase the specimen in a membrane, typically made out of latex, and we'll seal that in place with some O-rings like I've shown here. And there'll be plumbing in place that will allow us to have water flow in through the bottom, up through the specimen, and out through the top, and then out of the system. And we'll have burettes to measure the flow in and the flow out, and also the head applied on either end. We'll also have a line that goes to the cell as well, and we'll use that to apply cell pressure. And so by the cell pressure, we can control the total stress, or essentially the overburden pressure that would be felt by the GCL in the field. We can control the overburden pressure or cell pressure, which is in geotechnical terms, total stress. And we can also, by manipulating the pressure in these lines, we can change the pore water pressure as well. And in fact, sometimes we'll elevate the cell pressure and the pore water pressure an equal amount to essentially elevate the pressure in the system to so-called back pressure saturate the GCLs. That's very common in geotechnical testing. Not so important when testing GCLs, but it is something that we can do. Let's look at some photographs. Here's a real example. So here's a flexible wall permeameter in our laboratory. You can see the thin GCL here. We've got the latex membrane. We've got O-ring sealing it in place. We've got a top cap, and you can see the lines coming off of it with, these are Teflon lines, probably eluting some PFAS. These are the outflow lines because we flow from bottom to top, inflow lines below, and a cell pressure line you can see here just sneaking in the back. Now this is we make all our cells in our machine shop. We don't buy them, but a commercial cell might look a little more elegant, but it does essentially the same thing. We run these tests with ASTM D6766, standard test method for evaluation of hydraulic properties of GCLs permeated with potentially incompatible aqueous solutions. That's a mouthful, that title, but it's essentially the ASTM test method to do chemical compatibility testing. Important testing considerations: how we prepare the sample. Do we prehydrate it? And what's the effect of prehydration? What stress should we apply? How do we know when the test is in equilibrium? It's in hydraulic equilibrium, chemical equilibrium. Remember I talked about in the beginning that the definition of chemical compatibility is the hydraulic conductivity at chemical equilibrium. And it's compatible, the GCL is compatible if that hydraulic conductivity is sufficiently low for the application for which it's intended. So we need to get the hydraulic equilibrium, so the flow is steady, and chemical equilibrium, indicating that there are no more interactions occurring between the chemical in the inflow and the bentonite solid. We'll talk about how do we get at that. Well, often these permeameters, like I've shown here, and again, I apologize, I had a photograph of the soil specimen as opposed to GCL, we'll attach them to a so-called panel board. Panel board's got burettes, it's got a method to apply air pressures both to the effluent and to the cell pressure shown over here. We can apply the pressures and we can meter the flows, inflow, outflow using a panel board. Very common in geotechnical testing laboratories. Also allow us to do back pressure saturation that I mentioned earlier. One of the things we need to consider if we're going to be using an apparatus like this, a flexible wall permeameter attached to a panel board, these are relatively expensive panels, and if we're going to be putting strong leachates in them, we might damage them. So frequently what will be done if you're using a panel board is use something called a bladder accumulator. It's just a little vessel that's an interface between the burette and the panel and the leachate that's actually going into the specimen. You see a little Viton membrane right here. The upper reservoir will typically have the leachate in it, and the lower reservoir will have deionized water from the panel. So just a little separation technique to keep the panel board clean when we're using some nasty leachates in our experiments. You don't have to use a panel board. In fact, in my laboratory, we don't use them that often. We don't use elevated pressures that often as well, and I'll talk about why that is in just a moment. But what we'll use for influent is just a burette hanging, and we use gravity to drive the flow, as opposed to air pressure to push down on the water to drive the flow. So we have a burette here. It's got a flexible piece of tubing, and that kind of winds its way down into the bottom of the specimen. And I can't tell which line it's hooked up to. It looks like it's hooked up to, here's one here, coming down here, and then hooked up to this line going into the bottom of the specimen, flowing up and then out of the top. The simple method of using just burettes in a rack is nice because everything's driven by gravity. There's no air pressures, no pressure, air compressors to worry about, electrical failures. Just gravity's been steady for many, many years. This is a very highly reliable, simple system. We have probably 40 permeameters set up running in this framework at any given time. We'll use cell pressure. We'll either use that from a elevated reservoir that's at a higher elevation to provide more pressure, or we will use air pressure to elevate the cell pressure. We'll often collect the effluent rather than in a burette, just in an airtight sampling bag. This provides us with good control and allows us to really get a good assessment of the geochemistry with minimal alterations with the rest of the apparatus. So that's another technique as opposed to using a burette. One of the attributes of this I said I would mention is part one, I'm not using air pressure at all to induce elevated pressures in my specimen. So the pressures that are being applied, particularly the water pressures, are typical of what that GCL would see in the ground. And for just looking at hydraulic problems, probably not important. But when we change the pressure on the liquid, we potentially may change the geochemical interactions as well. And so we would like to use low pressure systems if we can when evaluating chemical interactions between leachates and GCLs so that we do not alter one, the chemistry of that leachate, or two, the interaction of that leachate with the solid surface in the bentonite. Here's just another example. Sometimes we'll use a common cell pressure line for a number of different cells, run them all up to the same source, but just to provide you another example of a number of GCLs and flexible wall permeameters undergoing chemical compatibility testing. Specimen preparation is very important in a number of different ways. This is an example of how we prepare specimens. We have a steel ring with a sharp edge that has the diameter of the specimen we want to test. We place that down on top of the GCL, and you'll see that we've wetted the perimeter just a little bit with some deionized water in this squirt bottle back here. That allows the bentonite around the edge, just around the edge, to osmotically swell and form a gel. So we seal in the bentonite that's within the gel, the GCL, and if we don't do that, we have potential to lose bentonite when we pull it out of the rest of the sample. The other thing that we'll do is I'll actually smear this edge. I'll actually take a little bit of that free bentonite that we see here. I'll blend that with deionized water. I'll form a paste, and I'll just wipe it around the edge of the GCL to have a nice smeared edge to seal up in the permeameter. Now let's put that GCL into the permeameter. And let's think about it. I showed it earlier where we've got a GCL between two end caps. Typically, in most conventional practice, we would put a porous stone between the GCL and the end caps, just like we would in a triaxial test. One of the troubles that we find with porous stones when we're setting up an experiment like this, particularly for chemical compatibility testing, is porous stones tend to get clogged, and they can get clogged during the experiment. The pores in a porous stone typically are much larger than in a GCL, but they are not large. And if you've worked with pore stones, you know how they can get clogged, how they can be difficult to saturate. There's no need for a porous stone when we're conducting tests, hydraulic conductivity tests for chemical compatibility of GCLs. I replaced that porous stone with a nice heavy non-woven geotextile. That's what I've shown here. A nice heavy non-woven geotextile, like a 12-ounce geotextile, non-woven, needle punched, lots of good capacity to conduct flow, large pores, good at distributing flow across the GCL, doesn't get clogged, easy to clean afterwards if we want to reuse it. And if it does get too clogged, we will discard it and use a new one. And in many testing laboratories that are testing GCLs, testing other geosynthetics, you've got non-wovens coming into the lab all the time. Some of that scrap that you get from testing other properties can be used to create discs for hydraulic conductivity testing. I really would encourage people to stop using porous stones and flexible wall permeation tests with GCLs, particularly for chemical compatibility testing. We just don't need porous stones in them, and they create problems. I think there are more tests measuring the hydraulic conductivity of clogged stones out there than we realize. I mentioned as well about putting paste around the edge. In some cases, when we're particularly worried about sidewall leakage, particularly if we got very strong solutions, some bauxite liquors, and we're dealing with some bentonite-polymer GCLs where the edge is a little hard to manipulate during extraction of the GCL from the GCL specimen from the GCL sample. We'll actually do a little bit extra. We'll create a paste, like I show over here. This is an ugly looking material, but it's a paste, deionized water, and the bentonite or bentonite polymer, and I put it right around the edge of the latex membrane on top of that lower non-woven geotextile, right around the edge, just to provide a good seal at the edge of the GCL. We have more tests that we run over for sidewall, have to reconduct or retests due to sidewall leakage than we would like. And this is one way we found to reduce that frequency significantly. There's a delicate trick to doing this. And this one's a little bit messy here, shown in the slide. You want to have enough bentonite around the edge, but not too much. You want to be judicious. Just have enough around the edge to form a good seal. And it takes some practice, and it's always easier said than done. But creating this little bentonite paste around the edge can do a lot to eliminate sidewall leakage. Okay, I'm getting my test set up. I've got my specimen in the permeameter now. I've been careful when I put it in there. I've used non-woven geotextiles instead of porous stones. I put some bentonite paste around the edge. Maybe I put a little bit down around the bottom as well, around the periphery, just to seal that off. I'm ready to get started. And I've got this leachate from my facility, but I don't have a whole lot of it. Do I need to use that site-specific leachate, or can I use a synthetic? Does it matter? The synthetic won't be quite the same, but if I get the chemistry right and we're really looking at chemical interactions, it should be about, we would expect it to behave similarly. And that's what our data show. When we look at tests run with synthetic leachates and real leachates, everything else being the same, we get very similar outcomes. A little bit more permeable with synthetics because they tend not to have as many suspended solids and other things floating around in solution that tend to clog pores. But a factor of 2 or so higher potentially, maybe a factor of 3, but not dramatically higher with the synthetic. So you can safely use a synthetic leachate that has essentially the same chemistry as what you measured in your actual leachate, recognizing that you're probably going to get an outcome that's a little bit more permeable than you would have obtained with the actual leachate for testing. And we've evaluated this for a broad range of leachates now and found it to be universally correct. What about stress? Now I decided I'm going to use a synthetic leachate. I got the cell set up. I'm going to permeate it with the synthetic. And I know I've got to evaluate my GCL at different stress ranges because there's an interest in what the hydraulic conductivity is going to be early on when we begin filling, when we first generating leachate, but also how it's going to behave over time. Do I need to run the test to completion at each stress? get it to hydraulic equilibrium and chemical equilibrium, and then ramp up the stress? Or could I run it to chemical equilibrium and hydraulic equilibrium at low stress, and then just increase the stress and do the test much more quickly? Well, as we'll talk about a little bit later, there's a real advantage to getting it to chemical equilibrium first at lower stress, and then ramping up the stress incrementally. The test time is quite a bit quicker. We will end up with slightly different results. If we run the test where we take it to chemical equilibrium at low stress and then increase the stress, we'll end up with slightly higher hydraulic conductivities, maybe a factor of 5. In contrast, if we run this specimen to equilibrium at each stress, chemical equilibrium, at the stresses that we're interested in evaluating, it will take a very long time, but we'll also get lower hydraulic conductivity. So more expedient, run the test at low stress, get it to equilibrium, chemical and hydraulic equilibrium, then increase the stress to evaluate how the hydraulic conductivity will decrease as the facility is filled, recognizing that there will be some error associated with that, and it will be on the conservative side. Now, another question I might have, I picked out my leachate and I looked at my stress conditions. Do I need to prehydrate the GCL? It's certainly not going to be completely dry when it first contacts the liquid. You know, and early on in many of the GCL testing, we would actually permeate it with deionized water first, right? And then we would stop the deionized water and replace it with leachate. That's so-called direct prehydration or full prehydration. That's not very realistic either, because in not too many facilities do we go out there and put the GCL down and soak it in deionized water before it contacts leachate. What really happens in most situations is that we put a GCL on a prepared subgrade, a compacted subgrade, and it will imbibe some moisture from below that's moving up through the subgrade into the GCL and causing the GCL to hydrate from that moisture moving up from below. And that's what, and you can run experiments to evaluate that. And that's what I've illustrated here. This is a compacted subgrade here, just a compacted fine textured material. That one's about optimum water content. I've got a GCL on top of it, a geomembrane, the same sandwich we would see in the field. I've got a plastic end cap on the bottom. I'll take another end cap on the top. I'll wrap it in a membrane, and then I will put it in a tank and apply like a cell pressure of about 10 kPa. And I'll allow it to come to equilibrium with the moisture in that subgrade sample. That's so-called subgrade prehydration of the GCL, simulating what would likely happen in the field. And in this particular example, I've got a tank with 10 different specimens at one time that we're going to subject to subgrade prehydration. They're all wrapped in membranes. They've got the plastic caps on the end. We'll fill that tank with water. We'll put a lid on it. We'll apply a 10 kPa pressure to that water, simulating the overburden pressure from the leachate collection system above it. And then we'll allow it to prehydrate, typically for about 60 days, simulating for what we might occur in the field, where we would have a liner gets completed construction. We submit the construction documentation report to the agency. We get an approval and the ability to fill. And that might take 2, 3, 4 months between those two. So we use 60 days as a 2-month typical criterion. If we look at the effect of that prehydration, it really has very little influence on the hydraulic conductivity. What I show in this graph here on the right is the hydraulic conductivity after prehydration to the hydraulic conductivity if I just permeated it directly with leachate, no prehydration step at all. And they're roughly 1-to-1. It's a little bit less permeable with prehydration, but not markedly so. And we don't run many of these subgrade prehydration tests. We do them on occasion when it's of interest at a particular project, but most of the time, based on the data that we've collected, the very modest effect of prehydration from the subgrade doesn't warrant going that extra step, but it is something you can do. If I directly permeate it, I should recognize I may be a factor of 2, 3 times more permeable than might actually occur in the field. The water content of the subgrade when we do that experiment can have a very significant effect on the outcomes. If we've got a relatively moist subgrade, you might expect that we'll get a very moist GCL, right? And a dry subgrade will get a much drier GCL under those same type of experiments, just depending if the subgrade is moist versus drier. And I show that here with a couple experiments we did, and we've actually compared these GCL water contents to what we get in the field. And these are actually some liners that we exhumed a number of years back that had been in service for about 5 years when we had the opportunity to dig them up and measure the water content of the GCLs. And the laboratory tests, these subgrade prehydration tests, actually replicate that field condition pretty well. So if we are going to do a subgrade prehydration test and account for that, we ought to get the water content in that test done in a manner that's consistent with what we expect in the field. Can we get benefit from higher levels of prehydration? We can in some circumstances. If we get the prehydration water content up higher, we'll get a lower hydraulic conductivity. That's what I've shown here in this graph, hydraulic conductivity versus prehydration water content. That tends to be more beneficial for more concentrated solutions, that as the prehydration water content will increase, the hydraulic conductivity will diminish. But it may never diminish enough to really create a benefit of significance that will allow us to consider the GCL to be chemically compatible. In general, I don't put much confidence in prehydration processes for providing additional efficacy or resistance to chemical compatibility of GCLs. I just haven't seen the benefits. So we're running the test. We've got it prehydrated, we got the leachate, we've got it all set up, we got the stress criteria, we're running the test. How long do we have to run it for? What are the termination criteria? We'll take a few more minutes to look at these. Well, these are spelled out in D6766. First of all, we want to make sure that the hydraulic conductivity is leveled off. It will tend to change early on in the test, and then we'll tend to level off. We want to make sure that we have a sufficient amount of flow through the specimen. D6766 has a default for 2 pore volumes of flow. Essentially, you've flushed out 2 volumes of voids in the specimen, at least 2 volumes of voids. We want to have steady flow, meaning the inflow of the specimens equal to outflow. And we want to have the electrical conductivity of the outflow being roughly equal to the electrical conductivity of the inflow. And we use that as a surrogate of whether chemical reactions are complete. If the electrical conductivity of the outflow is similar to the inflow, that means the chemistry of the outflow is similar to the chemistry of the inflow. And if those two are similar, then there aren't chemical interactions occurring as the leachate is passing through the GCL. It has come into equilibrium by that point. Other criteria that are not in 6766, but we use in our lab, we look at pH of the inflow and outflow. We look for those to be comparable between 0.9 and 1.1. And equally important is we can look at the effluent to influent concentrations. That's really, if we want to determine whether we're in chemical equilibrium, that's probably the best measure. Whether the chemistry of the effluent, actually measuring the chemistry of the effluent and seeing whether it's similar to the influent. Let's look at what the data might look like. Here's some examples. This is what we see for looking at just hydraulic equilibrium. Early on, the test hydraulic conductivity drops. It's kind of steady for a while, but this is a specimen that's being permeated with a dilute solution. It's slowly interacting, the bentonite is, with the ions in solution. The hydraulic conductivity starts to climb rapidly early on, and then at a much more gradual rate. And it's not out here until more than 60 pore volumes of flow that the hydraulic conductivity actually becomes steady. Wow, that's a lot of flow. Inflow and outflow roughly the same. Early in the test, there's some variability, but it tends to be relatively constant. But the conductivity takes a long time. So some of these experiments may take a long time to reach equilibrium. And here, roughly around 70 pore volumes of flow. 70 pore volumes of flow before chemical equilibrium. Now, could we draw a conclusion about this test out here, maybe at 30? Yeah, probably we'd be close enough. But to get to true equilibrium, here it's 70. Let's look at chemical equilibrium, another set of data. I've got the pH data here in green, and I've got the EC data here in purple, and we're looking at the data in the effluent, all right, effluent data for EC, effluent pH, and the lines shown here on the graph correspond to plus or minus 10% of the influent, essentially the equilibrium lines. And you can see for this example, well, it's about 40 pore volumes of flow to get to pH equilibrium or EC equilibrium. A good deal of flow for that experiment. Here's another example. We're looking at potassium concentrations in the effluent, similar graph, potassium concentration, pore volumes of flow. Early on, there's very little potassium in the effluent because it's interacting with the bentonite. The potassium in the influent is going into the GCL. It's interacting with the Montmorillonite surface, and it's staying on that surface, ejecting other cations that are actually coming out in the effluent. And we see eventually, though, it comes to chemical equilibrium because that bentonite surface can no longer bind any more potassium. But that comes out here on the order of 90 pore volumes. Wow, that takes a long time. And actually look at it carefully when there's no more trend and there's equality, it's up on the order of about 110 pore volumes of flow. Now, a geochemist might not call this chemical equilibrium, but for a geoenvironmental engineer, a geotechnical engineer, probably close enough. A lot of flow's gone through the specimen. I've got a couple more slides. I've shown all those other slides in the context of pore volumes of flow that really doesn't convey time, but time is important. These tests can take a long time to run, and I show this graph as hydraulic conductivity versus time. We see it starts off low, and this is a dilute solution, so it's got a very slow change over time. And eventually to get to equilibrium, it's about, this one's almost 2 years. Now that's on the very long side, because in part it's a dilute solution. In an industrial liquid, it's more concentrated. This would occur more rapidly. But we should plan for long testing times. It's not uncommon to have tests that take at least 3 months, sometimes 6 months to run, even longer in some cases. So be prepared for that. If we get an outcome that's not what we expect, particularly if it's much more permeable than we expect, we should check that to make sure we don't have a test error. One of the more common test problems is so-called sidewall leakage. I talked about earlier where we're putting that bentonite band around the edge and trying to seal up to prevent any leak around the sidewall. If we get a high conductivity, we should run a dye test to evaluate whether we indeed have sidewall flow. And that's what I'm illustrating here. We take rhodamin WT dye, that's water tracing dye, it's non-toxic dye. We spike the influent, we watch for it to come out of the effluent. As soon as we see it in the effluent, we tear the specimen down and we look at where the flow paths were. This upper photograph shows very clearly. Look at the sidewall leakage here. The flow is going right around the edge of the specimen, and that's why it was very permeable. What we should see is the flow going through the specimen, like I've shown here in this lower diagram. That's a flow path through the GCL, not a sidewall leak, and that is indeed corresponding to a high hydraulic conductivity. This is an actual GCL with high hydraulic conductivity. This is a GCL that appears to have high hydraulic conductivity because we had a sidewall leak. So if we get a high hydraulic conductivity, run a dye test, see if we have sidewall leakage. Let's take just a couple of moments here to finish. And I've spent the lion's share of this presentation talking about conventional bentonites. But I've also talked to you in other webinars about bentonite-polymer composites. This combination of bentonite and water, a hydrating polymer that work together to create low hydraulic conductivity, even in very aggressive solutions. And they function differently. I showed earlier with a conventional bentonite, if the bentonite doesn't swell, we have these large pores, and those pores become a preferential pathway, and we get high hydraulic conductivity. In a BPC-GCL, or bentonite polymer composite, we remedy this condition where the bentonite doesn't swell by adding a hydrating polymer or a polymer gel. And that polymer gel fills that void space. And the bentonite and the polymer work together to create a material that has very fine pores and very low hydraulic conductivity. They function by that polymer remaining within the pore space. If it's eluted, if it flows out of the system, the hydraulic conductivity will again become high. So they're a little different. So some things we should think about. Well, one thing, first of all, is that swell index is not a good indicator because it's not a swelling phenomenon that's controlling the hydraulic conductivity of BPC-GCL. It's that polymer gel filling the pore space. And I talked about this in the second webinar. There's been some literature that's come out recently which suggests that one of the reasons that the swell index is not a good indicator of hydraulic conductivity of BPC-GCLs is that the swell index method tends to bias the outcomes. We recently went back through all of our experiments in our database and ran the swell index with the method recommended in the recent literature that involves not crushing the material. And we still did not find a relationship between hydraulic conductivity and swell index, regardless of we measure swell index using the conventional technique with D5890 or the uncrushed technique that's in some of the more recent literature. We just don't see a relationship between hydraulic conductivity and swell. And in fact, if the swell index is low, we may have hydraulic conductivities that are extremely low and extremely high. If the swell index is high, we tend to get low conductivities, but it's really this range down in here where there's no swelling and yet we can have very different properties. And we may have GCLs that are very effective and yet just don't exhibit any swelling. So we need to be careful about drawing inferences about BPC-GCLs based on swell index alone. We really need to run the hydraulic conductivity test. I wouldn't run a swell index test on a BPC, find out it's low and reject that BPC as something I'm not going to consider. Our graph here would suggest I could have a very low swell index and indeed have very low hydraulic conductivity as well, regardless of how the swell index is run. Other things we need to pay attention to. When we run BPC-GCLs, we will tend to elute some of the polymer in the experiment. That can be a problem because it will collect, as I've shown you, these little yellow dots are the polymer. They will plug up pores in the geotextile. If we have a porous stone here, it will become fully plugged, probably more plugged than the GCL itself. The outflow lines themselves can become plugged as well. We tend to use larger 1/4 inch outflow lines as opposed to 1/8 inch in a lot of commercial cells, so that if we have anything entrained in the effluent lines, it can flow out of the system. If you're testing bentonite-polymer composites for chemical compatibility, be really careful that you don't have clogging problems. Flush the outflow system regularly. Do not use porous stones. Use a non-woven geotextile. Be very thoughtful to make sure that the hydraulic conductivity you're measuring is the hydraulic conductivity of the GCL and not of a clogged porous stone or a clogged geotextile or a clogged effluent line. Flush it regularly. Pay attention to the effluent. Make sure that you don't have clogging. This just takes attention and observation in the test, very clear and careful attention. So just a couple of concluding remarks and then we'll do some Q&A. Some implications for testing conventional GCLs. One, at the very beginning, understand the chemistry, right? Understand the chemistry. How should it affect the bentonite? And what hydraulic, how will it affect swelling? What hydraulic conductivity should I anticipate? Based on the chemistry that we see and the other data that we have. Look at the I and the RMD. Compare it to that chart that I showed earlier. Where does it sit relative to MSW leachates? Is it similar or is it very different? That'll give us a benchmark against which to draw some inferences. What about swell index? Let's use swell index as a good screening tool for conventional GCLs. If we have a calibration curve between hydraulic conductivity and swell index, it's wonderful. Fluid loss is another technique. I don't use that, but it works equally as well as swell index. Great screening tool. We can use that to screen out GCLs that are very unlikely to work and focus on those for hydraulic conductivity testing on GCLs that have a much greater chance of functioning appropriately. Plan for testing times. Testing times can be long. I showed things on the order of years. That's not that common. Maybe that's a little bit dramatic for a webinar, but it won't be done in a week or 2 weeks. Well, unless it's very permeable. It's going to take 3 months, 6 months, sometimes longer. Be prepared for that. Plan ahead and use screening tools if you can, like Swell Index, to avoid unnecessary testing. And I wouldn't rely on subgrade prehydration. That's done in some cases. I don't find that there a lot of efficacy in that. The stress reduction can be important, but that tends to be about a factor of 10. So if we end up with a GCL that's very permeable, even a higher level of stress probably isn't going to remedy that condition in a significant way. I tend to run most of our tests at about 20 kPa. And if I get a good outcome from 20 kPa, I feel confident in the application and other levels of stress as well. Some special nuances for BPC-GCLs, again, understand the chemistry, right? And go back to the previous webinar we talked about anions, how they can affect BPC-GCLs. Screening tests like swell index and fluid loss are not appropriate for BPC-GCLs based on the data that we see. There's some differences in the literature right now. I am convinced, as we've gone back and looked at our data again, rerun all of our swell index tests with the recommended procedures and some of the newest literature, we still don't see a relationship between hydraulic conductivity and swell index. I would not rely on that as a screening tool. At this time, we do not have a good screening tool for BPC-GCLs. We're working on those, but we don't have a really good tool. Watch for clogging. Pay attention to polymer clogging pore stones, platens, tubings. All those different pore spaces can get plugged with polymer. Flush the outflow regularly. Observe the outflow. Look for potential clogging. Do not use pore stones. I would avoid them if you can. I would use a nice, heavy, non-woven needle punch geotextile. 6766 termination criteria. I didn't talk about this in a significant way, but the termination criteria that we developed for 6766 are all based on conventional geochemistry of a mineral surface coming to equilibrium with a aqueous solution. They're not for polymers. We don't quite know what the appropriate termination criteria are for BPCs. That's an area that we're working on. And finally, like I said for the other ones, plan for a long time to run the test. They're not going to be done in a week or 2 weeks. Plan ahead, get your testing out early. So I'm going to conclude there. I know we've run a little bit late, but I want to provide some opportunity for you to ask questions. But I also want to acknowledge a bunch of people that have worked with me over the years that have all contributed to this. And this probably isn't a complete list, but there's a lot of students and colleagues that have contributed to us over the last 25 years that helped us generate this knowledge. So thank you to all of them. And we'll stop now and I'll take some questions. And I think I got to pop out so I can see the chat. Hope. So if you do have a question, just put it into the questions area and go to webinar. Will a recording be available on slides? Yes. We will have a recording and slides available after the presentation. We'll post both of those in the file share that I mentioned earlier. So look for that. And if you're on the list, you will get an email from me telling you where to find that. All right. Question from Thomas Brown. At what leachate calcium concentrations in milligrams per liter do you become concerned with insufficient swell? That's a more complicated question. I don't work in milligrams per liter that much. I work in millimole. So I'd have to go back. I will go back and respond to that directly and send an email to the group. But you can look at some of those graphs I showed earlier where the conductivity starts to take off in terms of molarity. For example, I showed early on where it was hydraulic conductivity versus concentration on the x-axis. That's in molarity, and just convert that over to milligrams per liter of calcium. All right, you can convert that over directly. And that, let me just go back and find that slide. So we're looking at about probably 20 to 30 millimolar is where the calcium tends to take off. So convert that over to milligrams per liter. I apologize, I don't know that off the top of my head. Question from Calvert Barclay. What do you think about considering degree of saturation as opposed to equilibrium water content? Yeah, good question. I didn't really talk about this, but usually we run these tests so long to get hydraulic and chemical equilibrium that they are completely saturated. One of the things I do check when I complete my tests is, and I don't very commonly run a B check, but I will calculate the degree of saturation based on weight volume calculations at the end of the experiment. They are inevitably within 90 to 110%. There's a little bit of error in that calculation. So I use that to check whether it's saturated. The final gravimetric water content, or weight of water over weight of solid, is going to depend on the stress condition as well. So you have to be a little careful using that as a equilibrium criterion. I don't normally report that, except for I report the final water content. Typically, trying to think of numbers that we see will, at the end of a test, 120, 130 for a chemical solution. Here's another question from Thomas Brown. Are there GCLs that can be used above pH 12 or below pH 2? Good question. Most conventional bentonites won't work in that range, although some will. I've got some literature on hyperalkaline solutions with some conventional GCLs. If you're interested, send me a note. I'll email you a copy of that. I'll actually stick them on the file share as well. But when we get in that extreme range, then we're usually getting to a bentonite-polymer composite GCL. So, for example, in the highly alkaline range, we frequently use bentonite-polymer composite GCLs for bauxite liquor. Bauxite liquor tends to have a pH between about 12 and 14, really alkaline stuff because they use sodium hydroxide to dissolve alumina. So there are commercially available bentonite polymer composites that work with those hyperalkaline conditions. Same thing with the highly acidic conditions as well. A bentonite polymer composite will work in that. You have to get the right polymer that's appropriate for an acid as well. If you're interested, I will place, we have a paper that we just published in the last few months about hyperalkaline solutions with bentonite polymer composites for bauxite liquor. I will put that on the file share, and I'll also put our earlier paper with a conventional bentonite with hyperalkaline bauxite liquors as well. Let's see if any other questions. I got a couple there from Thomas, a really good. Calvert. Sherry, anybody else have any questions? Well, okay, sounds like we need to wind it up. I know we're out of time. Went a little long, I apologize for that. Hopefully the information you found to be valuable. Yeah, I will post these slides. I will send you an email where to find them and the recording as well. You'll see that my email address, you'll get an email from me, so you'll have it, but it's also on my cover slide as well. Feel free to email me with questions. I mean, my role in the industry is to help answer questions and provide information. That's one of the things that I believe that is important for us as academics to do, is trying to serve industry to help make good solutions. So please, if you have a question, reach out to me. If you have many questions, feel free to keep asking. I'm glad to get them. I learn from your questions all the time, so feel free to send them in to me. Okay, I think we'll wrap up then. I see a few people dropping off as well. Again, make sure you're signed up with your name and email address on the attendance sheet so that I can get you a participation certificate and send you the information on where you can download the presentation, where you can download the recording, and where all the related papers and the like will be posted. And we'll close up now. Thank you very much for coming. I appreciate your time.